Friends, I think we are live. Let me just check the connection quality and get back to you. Just give me a couple of minutes, please. I'll just check if everything is working as expected. Give me a minute or so, and then we'll start the live session in a few minutes. Right? So just give me a couple of minutes, just to make sure that everything is working as expected. Yeah, so I can see my own stream. It looks good. No issues that I see now. So that's good news. First and foremost. So the second thing is, let me just adjust my screen and questions. Just give me a minute for that. Okay. Okay, so this whole thing is messed up, but that's okay. I'll just adjust everything. Just give me a minute or so. Okay, so these are our questions, the live chat. Okay, cool. So, okay, so we'll start the session in a few minutes. I typically come a few minutes early, just in case there are any technical glitches. So can you all please confirm if you can see the screen and hear my voice clearly in the chat window? Again, I have the chat window on my right so that I can see the answers that you folks provide. So can you please confirm if the audio and video are smooth? Please confirm that so that I'm sure that there are no glitches of any sort. Okay, so yeah, the speed is good. Okay. Yeah, sounds good. Okay, so most of you, at least some of you have confirmed that things are good. That's okay, not a problem. Okay. Okay, so everybody can see and hear me. Good. Again, we also have some of our mentors and team members who will be responding in the chat window. Some of the questions that you folks have, I'll also try to answer some of them. Cool. Good. So everything is clear. Before we start, a small announcement of sorts, because all of us are working from home. In case there is a power failure, because it's fairly cloudy and windy here in Hyderabad, where at least I'm residing for now. So in case there is a power failure, please be patient. We will try and join the same session as and when the generators kick in for us. And in case I cannot join the existing session, we'll create a new live session and join there. So just wanted to make sure that you don't have that issue. Okay, so in case there is any technical glitches because of power outage, please be patient. We will rejoin back. Okay. Cool. So let's wait. So it's 6:58. So since the announcement time is 7 p.m., let's wait till 7 p.m. We'll start the session now. We'll start the session at sharp 7. So somebody says, is it too late to start the preparation end of May? No, it's not. I mean, not at all. Actually, a vast majority of students actually start their preparation in July, right? If you prepare for GATE genuinely and work hard for a few months, that's more than sufficient. A vast majority of GATE students, again, we have seen a few toppers, people who have performed very well last year. Many of them actually started in June, July or so. So that's perfectly all right. The most important thing that you should look at is your dedication and persistent hard work. That's what matters. Because if you start now, or if you have started in February, but if you have not been persistent and consistent regularly with GATE preparation, it's useless. Okay, so again, people who start early certainly have an advantage if they're disciplined. Again, as we mentioned, we'll start the session at sharp 7 because that's the announced time. Some people might join at 7 p.m. itself, right? So let's wait for it. Will the GATE exam be postponed? Mostly no, but we don't know yet. We don't know how the situation will be next year, February. But I think the central government and all the major institutions are planning to conduct even competitive exams that are there this year, like IIT, JEE, etc., in a very smooth fashion. Of course, they'll come up with methodologies. So most likely it may not get postponed unless things become worse next year. Okay, sounds good. It's 7 p.m. sharp. So let's get started. Okay, so couple of 2 minutes of announcements before we go in. Just to be clear, this is an interactive problem solving session. It's the first of its kind. Now we are starting with data structures and algorithms, a very important and a very foundational subject. as we announced as part of the live announcement, these are the 4 topics from which we'll pick up some interesting problems and solve together. Okay. But before we go in, a very quick update. So from now on, we'll be conducting 2 live sessions per week for all of our course registered students, right? And the topics, again, we announced this video on our channel. In case anybody missed it, please feel free to watch it. So we will be conducting 2 live sessions per week starting this week. And there are 3 topics that we'll focus on. The first topic is problem solving, just like this session. Again, conceptual doubt clarification that we have already explained in another video, what we'll do in this. In this, basically, we'll take the best of questions that students ask us as part of when they send us emails or when they ask questions in the comment section or under our videos, and we'll clarify all these doubts corresponding to each of the topics across all subjects. Again, we'll do this problem solving, we'll do this conceptual doubt clarification for a bunch of topics in each session, but we'll cover all the subjects by the end of it. Then we have a bunch of miscellaneous topics, primarily to guide you on how to prepare better, how to practice better, how to revise better, etc. Right? So again, there is a video that we put out, if I'm not wrong, today morning on our YouTube channel. If you want more details, please check it out there. Just wanted to make this clear. Again, some of the sessions will be publicly available like this one, but there will also be private sessions limited only to our course registered students as we go. Okay, I think, okay, let me just do full screen. Okay. Okay, my bad. Okay. So this is the first question, folks. Okay. So let's start getting into the problems themselves. This is the first question. Please take a couple of minutes. Let me also start a timer here. Let me just start a timer. I hope everybody can see this question, or else let's skip the timer because we are not yet there. I mean, I don't want to force anybody. I'll start a timer on my watch, on my phone. Take a couple of minutes. Again, we are not giving any hard problems today. So just take some time. Let's start the session itself. We have 8 questions. In the interest of everyone's time, take this question. Please suggest the answer. Please put in your answer in the comment section or in the chat window. Right? So again, I'll explain the solution also in a few minutes. Again, let's get into the problem solving itself. This is the first question. Take a couple of minutes. Again, this is a fairly easy question. The most important thing that we often see is that students rush to answer. Please don't rush. It is important for you to get the correct answer in a reasonable amount of time. Take your time, answer it. We'll give it a minute or 2. Again, since we are still early in the preparation, GATE exam is still a few months away. So time is not important. It is the conceptual understanding and getting the answers right that is important. So it's 1 minute up. I do see some answers here. Okay, I see couple of answers, primarily 2 options that people are picking, which is good. I'll clarify the answer. Okay. Let's wait for others also to answer. So it's about a minute and a half now. So again, if you have not answered by now, that's okay. Just think about it. And in the interest of time, I'll explain the solution also. Okay. So, okay, let's go. Let's go into the session itself. Sorry, this is misbehaving. So just give me a second. Let me see if I can get my mouse to work as expected. Just a second, folks. Just a second. My mouse is stuck for some reason. Okay, now it's working. Okay, so it's working now, thankfully. Okay. So let me just explain the solution for this. It's a fairly simple problem. Assume that we are using the merge sort algorithm. Sorry, so this is the second question. I'm sorry, my bad. Okay, my mouse for some reason. That's okay. That's okay. We'll have these glitches once in a while. That's okay. No problem. So let's go with this question. The insertion sort goes sequentially. So it's explaining what the insertion sort does. The core idea here is that instead of using the sequential search, we are using the binary search as part of insertion sort. What would happen to the time complexity? That's the question here. Of course, here we are talking about the worst case time complexity. How does insertion sort itself work? In any iteration I, right? In any iteration I, you have all of these previous elements already sorted. So we try to take this element and try to place it in its appropriate position. Now to find the appropriate position of this element, right? Instead of using sequential search, which is how we actually do it in insertion sort, let's assume we perform binary search, right? Instead of doing sequential search, which means instead of comparing this element with all these elements, let's assume we perform a binary search, which means I can find where this element should belong to in log n time, or log I time to be precise, because there are I minus 1 elements here, right? So there are I minus 1 elements here. In each, again, this I goes from 1 to n. But once you found, so let's assume you have to place this element here. Let's assume this is the index where you have to place it. But then when you place it here, you have to move all these elements that you have to move them to the right also. So how does insertion sort work? In each iteration, you pick the ith element, you do a sequential search to figure out where to place it, and then you place it there, and all the other elements, you move them to the right. So binary search helps us to determine where to place this in log of I time, but since I have to move all the elements which are on the right side where this element is placed, I have to move them to the right. In the worst case, I might have to make I moves. So I elements might have to be moved to the right in the worst case. And this is for the ith element. So when we use sequential search, what happens? My search time worst case can be order of I, and then to move will be again order of I. Here my search time has reduced to log I, but the movement is still worst case I, which means the total time complexity would not change even if we use binary search. And that's why we don't use binary search as part of insertion sort, because it doesn't materially impact the worst case performance, right? So hence, because in the worst case, in each iteration, you might have to perform order of I operations. Even though the search is log I, the number of movements of all the elements to the right is order of I. So in the worst case, if you sum I from 1 to n, you would get order of n square, or theta of n square. Okay. Again, the important thing here is I'm assuming that you know these concepts. That's why I'm not explaining you how insertion sort works in depth. Right? I'm just explaining the solution here. Very simple. It's a good question actually. It's a simple but a good question. Okay. Very simple, easy actually. Okay, cool. So this is the first question. Now let's go to the second question now. Again, those of you who got D, most likely you're getting confused. Again, D and C, this is the confusing possibility. Okay, a lot of people would get confused and choose D, while C is the right answer, because people think, okay, that insertion sort only has the search part, right? Insertion sort has two parts. First, you perform a search to determine where to place the ith element, and then you move all the elements to the right. They ignore the moving the elements to the right. That's why they might fall into the trap and say order of n log n or theta of n log n. A very common mistake, but that's okay. It's okay to make silly mistakes now and learn from those mistakes so that in the examination a few months from now, you don't make those mistakes. Right? Simple problem. Okay, let's go to the second problem now. Okay, please. The second problem is here. Take about 2 minutes. Let's take 2 minutes because you might have to use a calculator for this. Again, you might need a calculator for this, so please use it if you have to. Take your time, guys. Please don't hurry. Getting the answer right is important than being the first person here. One minute up. We have one more minute. Again, this is also a simple question. Take your time. It's okay. So 15 more seconds. Try to put in your answers now. Sorry. Okay, so the 2 minutes are up, but in case you haven't been able to answer, that's also okay. Let's try to answer this step by step. Again, assume that merge sort algorithm in the worst case take 30 seconds for an input of size 64 on some processor, right? So we know that the merge sort algorithm has a time complexity of order of n log n, right? Again, log base 2, right? So that's the worst case time complexity of merge sort. Now what it says here is, so when it says order of n log n, what does it mean? It means, I mean, if you simplify it, again, there are some simplifying assumptions that we have to make to answer this question. So one simplifying assumption here is that the actual time complexity, this is again in a big O notation, you can approximate this and say there is k times n log n, right? Again, log base 2 here. Again, I preferably write LG for log base 2. That's a simple notation, right? So k, again, this is the time it takes. Again, here if what is given to us, the input size is 64, which means when n equals to 64, this value equals to 30 seconds. Again, we are making some approximations here. Okay, we are saying if it's order of n log n, we are assuming that it is k times some constant times. K is our constant, right? So here we know what n is. Again, log 2 n. So this whole part is simple. So if you simplify this and if you plug n here as 64, right? Just simple, plug it in a calculator, and what will you get here? K into, so you'll get k into 384 equals to 30 seconds. And now if you simplify this, you get k equals to 30 by 384, right? This is what you get. Now what is the question? Which of the following most closely approximates the maximum input size of a problem that can be solved in 5 minutes? Now what is 5 minutes? Again, all of our notation is in seconds. K is this when we used seconds. So please don't use minutes here. Let's use everything in the same units. 5 minutes is 300 seconds. If k equals to this, now what do we have? K is this. So k into n log n equals to 300. This is what we have, right? Now if you simplify it and compute for n, again, there are two ways of doing it. Look at this. All these are 2 power something, right? So all these are 2 power, this is 2 power 8, 2 power 9, 2 power 10, right? 2 power 11. So all these, so computing the log n base 2 is also trivial here. Say if you solve for n here, you would get n equals to 512. Just a simple numerical computation here. Again, we are making some basic assumptions that whenever the time complexity in the worst case is order of n log n, we can simplify it to k into n log n. This is an assumption. Again, it's a reasonable assumption to make, right? So the answer here would be B, right? So 512 is what you would get. Again, I solved this problem earlier and put it in my notes so that I don't make silly mistakes when I'm solving them. Some questions I have solved, some questions I have not solved. So if I make a mistake, please do let me know. So the answer here is 512. Simple question. All you had to know was what is the worst case of merge sort, and you had to make this small leap here that whenever the worst case time complexity is order of n log n, and we are actually given numerical values of n and the actual time, we can simplify for k. That's the only small leap in problem solving that you have to make. Okay. Again, some people might say, hey, you're making a very simplifying assumption. So order of n log n could also be order of n log n plus n, right, into some k. Right, so you can make many of these assumptions. So given this problem, again, such problems have been asked in the past in GATE. Again, solving this problem will become much harder. So you make a simplifying assumption that whenever you have n log n, you simplify to k into n log n. This is a simplifying assumption. Okay, cool. So let's go to the third problem now. Cool. So let's get into it. Okay, so this is the third problem. Again, simple, straightforward problem. Let's see. Again, take a couple of minutes. Okay, I'm starting the timer. Take a couple of minutes. Hey, I think there is a mistake somewhere. 1 second, folks. Some of you are saying, 1 second. Some of you are saying it should be 6 minutes instead of 5 minutes. I'll check that. So 1 second. Let's actually do the math, right? So why not? Okay. So I think there is a small, there could have been a typo. So let me just do this. Okay. So we know that, okay, where was our, okay, let's solve it, right? K equals to this, right? So let's actually see this. If this is n log n, so what do you get? Let's solve this, right? Shouldn't be hard. So you have n log n here. N log n is, you take it that side, right? So you have n log n, 300 by 30, which is 10. So you get 3840, right? If n is 512, what happens here? This is 512 log n. This is 2 power 9. So you get 9 here. So what is this? Okay. So this is not working out. So I think it should be 6 minutes. Sorry. I think there is a small error here. If it is 6 minutes, then it would work out. I think there is a small typo in the question. Sorry for that. If this is 6 minutes, it will be 360 seconds. So if this is 360, then this is roughly how much? This is, so if this is 360, this is 12. Yeah. Okay, so let me just quickly calculate this. 3840, sorry, I'm just using a calculator to solve it. So if this was 6 minutes and not 5 minutes, sorry, if there is a mistake, let's just solve it together, right? So 360 by 30, which is 12. So 384 into 12. What is 384 into 12? I'm just using my calculator. 4608. And what is 4608? Yeah, so it should be 6 minutes. I'm sorry, my bad. I think we made a mistake when we were setting this question. Sorry, it should be 6 minutes. Yes, you're right. Sorry for this mistake. It should have been 6 minutes and the answer is 512. Sorry for the typo. Sorry. Okay, cool. I'm glad some of you, again, if there is any mistake, please do point it out. We'll solve it together. Okay. Let's go to the third. This is the next problem, right, that we started off with. Again, please take your time. This is the third problem. After a while, I'll give you a hint. I think that might be a good idea. This is a simple, straightforward problem. If there is any mistake, do let us know. We'll correct it. Again, since it's been a minute, one hint for those of you who haven't yet solved it, please use master theorem. Again, if you know master theorem, this should be simple and straightforward. Okay, so many of you got it, which is good. So let's look at the answer. Again, whenever we encounter a problem like this, it's actually Master's theorem. The way I personally like it is I write down the Master's theorem. I'm very bad at remembering equations personally. Again, some of our teammates are terrific with it. They can remember this like by heart. I can't, to be honest with you. So I write down the Master's theorem, right? Very simple. If this is the form, you just have to check A and B power K. There are three cases. If A is less than B power K, A equals to B power K, A is greater than B power K. This is one of the variations of Master's theorem. Very simple theorem. Now in our case, what do we have? Look at our problem. Okay. So look at our problem, what we have. We have A as 2. Look at this. We have A as 2, B also as 2. This can be written as n power half, right? So K can be half and C is constant. C is 1, right? So what do we have here? So if you think about it, what do we have? We have A equals to 2, B equals to 2, C equals to 1, K equals to half. Now what should we do? We should just compare A with B power K. What is A here? A is 2. Just compare A with B power K. B is 2, K is half, right? So 2 versus 2 power half. 2 power half is nothing but square root of 2. So A is greater than this. So the moment you have A greater than B power K, this is what your Master's theorem says. Now let's see what this works out to be. Theta of n power log A base B. What is A? A is 2, right? So log 2 base B. B is 2, right? So log 2 base 2 is 1. So this is nothing but theta of n power 1. That's it. So if you know Master's theorem, very useful to solve problems like these. And similar problems you will encounter very common questions that you see in GATE. Only thing is, if you're good at remembering these equations by heart, great. If you're not like me, I typically try to write these equations down. Again, I do it all the time. And I compare. Once I write this, I'm more confident. Otherwise, I've done silly mistakes personally, right? So just compare A with B power K and you're done. It's that simple, right? Very simple solution. So it is, what is the answer now? I forgot what the, okay, 1 second. So it is order of n, right? So D is the answer, right? So D is the answer, order of n. We just solved it now. Order of n is the answer. So some of you got confused with others. Again, it's all about simply applying the Master's theorem. If you know the Master's theorem and if you've not made a mistake in applying it, Master's theorem is all about figuring out what your A is, what your B is, what your C is, what your K is. If you know these 4 parts, you can trivially solve it. There are just 3 cases, right? So let's go to the next problem now. Again, somebody is asking a good question. Can we solve it using the recurrence tree approach? You can, but that would take too much time. In an examination, if there is a simpler way to solve problems like this, you should try and solve it. Again, if you follow the recurrence tree based method, right? If you use the recursion tree or the recurrence tree based method, it would take you too much time. You're basically trying to arrive at the Master's theorem. You're trying to prove Master's theorem in an examination. What is the point in it? The reason we have Master's theorem in an examination setting is, again, such questions are typically 1-mark questions, right? So because people expect you to know Master's theorem, not derive it in the examination. So you can solve it using the recursion tree method also, but that would take too much time. That will be equivalent to deriving the whole Master's theorem itself, especially this case of Master's theorem, right? So you'll be deriving this case of Master's theorem, which is not appropriate in an examination like GATE. Okay, cool. So even though if you have bad memory like me, it's still a good idea to remember Master's theorem. Okay, so let's go to the next problem now. Cool. Please read it. Let's take a couple of minutes. This is a slightly lengthy problem, so let's take 2.5 minutes. Take 2.5 minutes. Don't make silly mistakes. Be careful. I guess that was the police van doing sorties to ensure that everybody is in-house. Everybody is in their homes because post 7 p.m. in Hyderabad, we are not allowed to step out. It's 1.5 minutes. Again, I'll give you a hint here. Please use Master's theorem again. Again, 30 more seconds. Oh, I see answers all over the place. A, C, B, D. Okay, it's 2.5 minutes. So let's look into the answer, right? Again, whenever you see something like this, whenever you see it in this form, right? Look at this. You have A, you have B here, you have your K, and this is your C. K is 1 here, right? So this is in a very simple format in which you can apply Master's theorem, right? It's actually fairly simple, right? You just have to apply Master's theorem on this, Master's theorem on this, Master's theorem on this, and get the result. It's that simple. The reason it takes more time is because you have to apply Master's theorem on 3 different recurrence relations, right? So I've written it down actually here. Look at this. This is your A, 4, 8, 16 respectively. Your B's are 2, 3, 4. Your K is n power 1, 2 and 2. This is your C's. C is 10, 24, 10. Now first let's look at the first one. What do you have to compare? You have to always compare A with B power K. That's the logic here, right? So what is A here? A is 4. What is B power K? B is 2, K is 1. Right? Look at this. Again, if you know the Master's theorem, this is trivial. Now, when you compare A with B power K, A is greater than B power K. Now, again, when you have a problem like this, when you have A greater than B power K, you just apply this. You just apply this here. If A equals to B power K, just apply this. If A is less than B power K, just apply this. You just have to apply these three cases here. That's all there is actually. Okay, so that's all there is. So here A is greater than B power K, here A is less than B power K, here A equals to B power K. Right? So all the 3 cases are handled here. So this question is to ensure that you know all the 3 cases of Master's theorem well and you can apply it to simple problems. Now look at this. So what do we have here? We have A equals to B power. So this is A is greater than B power K. Right? So that's what we have here, right? So if A is greater than B power K, what is it? The answer should be theta of n into log A base B, right? So log A base B. Yes, it should be this. So what is B here? B is 2. What is A? 4. Right? B is 2. A is 4. So log 4 base 2 is 2. Right? That's what it is. This is n power. This is n power. So this is nothing but 2. So you get order of n square here. The second one, A is less than B power K. So when you have A less than B power K, what should you do? It's just basically theta of n power K. This is the first case, right? What is K here? K is 2 here because you have 24 n square, right? So the answer here is n power 2. You got it. The third case, what is third case? A equals to B power K. When you have A equals to B power K, what does Master's theorem say? It says theta of n power K log n. What is K here? Look at this. This is n square here. So K is 2. So you get theta of n square log n. Now amongst theta of n square, theta of n square and theta of n square log n, which of them grows fastest asymptotically? Obviously C. Right? Obviously C. This is the fastest growing. So this is also a simple problem. It is slightly time taking. That's why I gave you 2.5 minutes to solve this problem. You just have to apply the Master's theorem. All the 3 cases of Master's theorem are handled here. It's slightly time taking, but if you know Master's theorem, you can actually solve it in 1 to 1.5 minutes carefully. Again, you have to be careful. Okay, again, different people might learn Master's theorem with different names here. So I'm just using one here. That's why I've listed down the Master's theorem carefully here. Different people might instead of A, they might use alpha, instead of B, they might use beta. So everybody has their own formula. Again, the variable names might change, but the logic is the same. Okay. Okay, let's go to the next problem now. Okay, cool. Again, this does not have ABCD options. Please write down the answer. In an examination, actually, you'll be given ABCD options. Let's take 2.5 minutes for this. This is slightly lengthy. No, it's easy. You have to be careful, but it's not lengthy. Sorry, it's lengthy. It's not hard. I'm sorry. Okay, I see some answers being posted by folks. Let's see. Again, it's very easy to do silly mistakes once you're given code snippets like this. So please handle all the boundary cases. It's okay, even if you have not covered linked list, try it. Let's try it. This is simple C programming with pointers and structures. Of course, the linked list logic also. Remember that it's a singly linked list. Two minutes up, take 30 more seconds, it's okay. Please be cautious before you put in your answers. Okay, so yeah, we have overshot the 2.5 minutes. Again, this is simple. If you look at it, again, the moment you see any code like this, try to understand what's happening in the loop. Don't panic. Again, sometimes you could get very lengthy code. This is just defining the structure of a node in a singly linked list, the value and the next pointer. Again, some basic checks here, and the loop here. Look at what the loop is doing here. Again, you have to be careful. You have to run it step by step. Essentially, what's happening here is that two consecutive values are getting swapped. So if you have 1, 2, 3, 4, 5, 6, 7. This whole loop, basically, if you look at this snippet of code, again, you have to go line by line to make sure that you're not making a mistake, right? So what it's doing here is it is swapping these two elements first, right? And then if you look at the code logic here, especially this part, if you look at the code logic here, it swaps these two at the end of the first iteration. Look at this, your P is pointing to the first element, your Q is pointing to the second element here. Look at this, at the very beginning, Q is pointing to this, sorry, P is pointing to this, Q is pointing to it. Here we are swapping P and Q. Basically, you're basically swapping these two. But then the way the logic is written, because the loop here is on Q. The way the logic works is once it swaps these two, then it goes to the next two elements. So at the end of first iteration, okay, so the way it look is this. Again, I've written down the steps here. So this is the initial singly linked list, right? This is initial sequence of values in the singly linked list. At the end of first iteration, what happens? This will be your P, this will be your Q. So they both would get jumbled up. Okay, they both would get jumbled up. So, or they both would get swapped. That's what I mean, not jumbled up. I mean, they both would get swapped. So at the end of first iteration, these two would get jumbled up. Then your P and Q will be pointing to this. Then these two would get, in the second iteration, these two would get swapped. Again, that's the logic here. Again, this step is very important because this defines what Q will be, where this whole loop will terminate. Okay, that's the logic here. Okay, again, these are these are basically boundary cases. What if the list is empty? What if the list has only one element, and all those cases? This is your boundary case handling. Okay, this is basically your initialization of the loop. This is where the whole loop is running. Okay, so in the second iteration, what happens is these two will get, look at this, these two will get swapped, and then your P and Q will go here at the end of second iteration. At the end of third iteration, look at this, while Q is still not pointing to a null. So Q is still pointing to some memory cell, right? So now in the third iteration, what happens? Again, these two would get swapped with each other, right? So you get 5 and 6 will become 6 and 5. Next, here comes the tricky part. Here you have your P, right? So here you have your P, your Q will point to null now. Because your Q is pointing to null, this while loop will terminate. So by the end of it, what we would have is 2, 1, 4, 3, 6, 5 and 7. Again, whenever you see code like this, it's good to understand at a high level first. This is the representation of a node. This is basically the boundary case check. This is the initialization. In the while loop, you're doing a swap and then you have this simple logic to update Q. Because Q is the variable that is being used to iterate on. That's it. Right? So just given any code like this, first break it down, read the code carefully. Once you get the logic, it will be straightforward. Right? Again, I think most of you got it right. Somebody said it will also have a value 0. I don't know how they got a value of 0. Again, this is also a type of problem where you could do silly mistakes if you're not careful with the code. Right? Cool. Let's go to the next question now. This is again a very simple, very good question actually. This is a 1-minute question. Okay, this is simple. Again, if you know the basics of radix sort, this is trivial. Yeah, so again, all you have to know here is that radix sort, right, requires a stable sorting algorithm. At the end of the day, it requires a stable sorting algorithm to be used to sort the individual digits. Now, amongst these three options, quicksort is unstable. Again, we discuss in our course videos what is a stable sorting algorithm, etc. Quicksort is a very good example of an unstable sorting algorithm. The other two are not. So you cannot use quicksort. That's it, very simple. Again, some of you seem to have a question with this last line of code here. Look at what the last line is saying. It's saying, look at this, Q will be assigned to. This is a ternary condition, right? Again, whenever you see a ternary condition, please don't get confused. Okay, ternary condition is just like if else condition. This Q will be equal to P. Okay, see, look at this, P question mark. Okay, is P equals to null? Look at this, is P equals, see, this is basically if this condition, whatever is there. So how does ternary condition work? If this condition is true, this will take place. If this condition is false, it will take this. Simple logic. So Q, see what I told you just a while ago that this is basically an update statement on Q. So Q will be assigned either this value or 0 based on what P points to. Simple logic. Okay, nothing hard. Again, it's not double equal to. So just ternary statements, this is the condition. If it is true, this will be executed. If it is false, this will be executed. So Q will be equal to P next if P is not equals to null, otherwise it is 0. Just again, whenever you are confused with this, try to write it as an if-else statement. Again, I do this whenever somebody gives me a complex thing like this. I try to write it like a if-else statement because it's much more readable. It's easy to think through that. Okay. So I think that's a confusion that some of you had in the previous question. Okay. This question again, we just solved it. It's simple C because quicksort is unstable. Very simple question here. Very straightforward question. Okay. Let's go to another question. Let's take a minute and a half for this. This is our 7th question. Again, this is a simple, straightforward problem if you're careful reading the code. This whole thing is inside this for loop. I think there is a small indentation problem here. Okay, yeah, so minute and a half up. Again, this is a very simple question if you're careful, if you read the question carefully. Look at this loop. Okay, what is the time complexity of the fragment? This loop, I is getting incremented by 1, which means this will run order of n times. What about this? This is going from, look at this, this is going from I to j n minus 1. So j equals to I. Look at this. Whatever I value is, this is going from j equals to I up to n minus 1. Again, it's incrementing with j++. So asymptotically, if you think about it, again, we've seen similar code in our course videos when we explain insertion sort and concepts like this. So this total, these two loops together is order of n square, right? So these two loops together, right? Because we have seen a very similar code, j equals to I, j less than equal to n minus 1. Very similar snippet of code that we have seen. First, let's focus on these two for loops. These two for loops will execute for order of n square times. Order of n square times. We know that. Now the third part, this snippet of code is the interesting one. This snippet says I'll go from 1 to n. This is not dependent on j or I. Look at this. This loop is starting from I and going up to n minus 1. This loop is going from 1 up to n. But the update here is not linear. The update here is it's getting multiplied by 2 every time. So whenever you have this multiplication by 2, that means you have log n. Right? Basic logic. The moment you see something like this, this implies order of log n times. So these two loops together will run order of n square times. This internal loop here that we have, this runs order of log n times. So it's order of n square into log n. So order of n square into log n. Very simple question. Again, we have seen this type of twin loop, for within a for with I equals to this, j goes from I to n minus 1. This is standard. This we have seen in our course videos. Within this code snippet, look at what is here. This part is the interesting part. Again, this part is order of log n because if you look at binary search, this is how binary search looks like, right? If you think about it, binary search keeps jumping by half sizes of sorts, right? So you can think of this as running in order of log n times, a total of order of n square log n. Very simple question again. Okay. Again, most of you got it right, which is good. Okay. Next question. Think about it. Let's take a minute and a half for this also. Okay, there are a wide spectrum of answers from A, B, C, D. So just think through it. Okay, so we have completed 1.5 minutes. So let's go into the solution. It's actually simple. Okay, so let's go into the solution. So imagine if we use a singly linked list. So there are two lists, L1, L2. L1 points to the head of the singly linked list. The last one points to null. The last one points to null. So let's start with singly linked list, right? If we were to merge these two lists, right? If we want to concatenate these two lists, okay. So so we have to change this pointer. At the end of the day, linked lists are all about pointer changes. So we have to change this pointer and make this point to this. But because in a standard singly linked list, we don't have the pointer to the last element. We only have the pointer to the first element in a default singly linked list, right? So since we don't have a pointer to this, to figure out the whole because we don't have a pointer to the last element here. Suppose we want to concatenate L1 followed by L2. So what we have to iterate through this whole list and go to the last element and figure out the last element in the list by seeing if the next element is null and then adjust the pointers here. So the time complexity, if it was singly linked list, the default singly linked list where we have pointer only to the first element is the time it takes to traverse through the linked list here, the first linked list, which is not order of 1, right? So certainly this is not the answer. Now the moment you get this concept, the moment you understand this concept, now let's think quickly, okay? Because you got the gist of it, you got the core idea. Imagine if this was a doubly linked list, would it work now? If this was a doubly linked list, of course, this will point to null. If this were a doubly linked list, still, okay, so if this were a doubly linked list, so this will point to null. Even if this were a doubly linked list, we have to adjust this pointer to point to this, and we have to make this pointer point to that, right? So there are two pointer adjustments, but still we only have pointers to the first elements in a doubly linked list by default. We don't have pointers to the last element, and hence we still have to traverse through the whole thing. So even a doubly linked list won't work, but a circular linked list will work. The reason circular linked list works is because circular doubly linked list, I'm sorry. The reason a circular doubly linked list will work is because we have these pointers. We have this circular pointer, right? And we also have this pointer. So this pointing to this, it's a doubly linked list, right? It's a doubly linked list. Because in a circular doubly pointed, in a circular doubly linked list, we can arrive at the last element very quickly, right? We can arrive at the last element of our first list by just using the previous pointer here. Now, once we get this, look at this, once we get this, we can adjust its pointers and connect it to this back and back here. That's all we have to do, right? Again, again, we have to adjust this pointer also because we have to construct the circular doubly linked list again at the end of it. Again, this pointer also we have because in a circular linked list or a circular doubly linked list, we have this back pointer also, right? So at the end of the day, if we can access the last elements, if you can access the last elements in order of one time of both the lists, then we can implement the concatenation in order of one time. Now, the only way you can do it is if you have this backlink and you also have this backlink here, right? So you need the doubly linked list, which is also circular. Simple concept. Again, array implementation also won't work because imagine if I have an array implementation for list 1, array implementation for list 2. Let's assume there are 4 elements here and there are 3 elements here. If we want to concatenate this, we might have to allocate memory again and copy each of these values here, right? So again, that will be order of the number of elements that are there in L2, which will not be order of 1. So even array implementation won't work, singly linked list won't work, doubly linked list won't work, circular linked list is what works. Simple concept, nothing very hard here, right? So again, these are some of, again, we are starting with simpler problems. Some of you may think that these are very simple problems, but we are starting these sessions with simpler problems because anyway, we plan to do 2 sessions every week, either problem solving or conceptual clarification sessions. And as we progress through it, still we are in the early May, the first week of May, right? So as we come closer to February, as we move closer to the exam, we'll keep increasing the complexity of problems. The reason for that is, especially when you're learning the concept the first time, when you're practicing these problems, there is no point in jumping to very hard problems and get discouraged. Again, these are not too simple also. Some of them have actually been asked in GATE or very similar to questions that have been asked in GATE in the past, right? We are not giving too hard a problems right away, but we'll slowly increase the complexity of problems as we near the exam, right? So the next session that we have, which is also publicly available, is on 9th of May, which is Saturday, right? 9th of May is Saturday, if I'm not wrong. Let me just look at my calendar. 9th of May is Saturday. Again, 9th of May, again at 7 p.m. on our YouTube channel, we'll conduct a public live session. Again, it's a problem solving session again. The topics will be these, right? So in about 50 minutes or so, today we solved 8 problems. Again, we'll start with 8 problems and slowly we'll increase to 10 problems. Again, remember that we are not timing much now, but slowly as we progress, as we solve all the subjects, all the topics once, as we progress and we get closer to the examination, we will be more stricter with the timing, right? So this is one of the types of live sessions that we'll be conducting. And please, for the 9th of May session, please prepare the basic stacks and stack operations, queues and arrays, searching, binary search trees, heap sort, basic concepts, and balanced trees and hashing, right? We'll again try to solve about 8 problems now, but as we progress through these live sessions, we will try and do 10 problems. Again, any mistakes, I think there is one mistake that was pointed by one of the students that I was reading in the comment section. I think there was some problem here, right? About initialization of I or something like that. Somebody mentioned that. We'll, again, any errors, if there are any errors, we'll correct them step by step. Please do point them so that we correct those errors. Just like the 6 minutes error that we made. Again, we'll be careful as we progress through these. This was supposed to be 6 minutes and not 5 minutes. But that's okay. We'll make some small mistakes. If we make mistakes, with the help of you, we'll correct them also. Okay. So again, 9th of May, which is the coming Saturday, please prepare these 7 p.m. same sessions, 8 to 10 problems. We'll probably do 8 easy to medium problems. Same setup. Okay. See you again. Thank you, folks. Thank you very much.